Fantastic. So now that we are at a place where we understand the fields that we're working with, understanding that there are spatial fields, like I indicate you with the X, Y, and Z. So U has got a U, dark U here, or bold U, is a vector of fields, and the one field is U, X, Y, Z, other one is V, X, Y, Z, and other is W, X, Y, Z. And when I use the word field, what I really just mean is just a function of X, Y, and Z. Okay, some expression of X, Y, and Z that we need to have. That is really what this means. Okay, but now that we understand what displacement fields are, we're comfortable with how to compute strains, comfortable with the stress tensor, making sure we understand what it means, how it relates to forces that we apply by attractions, so that sort of journey, how they transform, how do we conduct linear superposition with them. All those things we should be fairly comfortable with now. Okay, so what I've just put up here on this concept card is really just to give you an overview of what I expect of you if I were to supply you with a displacement field, and I tell you about the problem. So typically what I will do is I'll say, here's a displacement field, and here's the problem that I claim this displacement field is the solution to. You need to be able to tell me whether I'm talking rubbish or not. Okay, and tell me which things are consistent, which things seem to be matching up with the description of the problem, and which things are not matching up. So either they are just wrong, or maybe they are just an approximation, and then you need to be able to make a judgment call. Okay, but and it won't be anything blurry, or it will be very clear cut. If I claim something is in bending, but I give you something that's in uniaxial tension, that's clearly not just an approximation that went wrong. That is clearly just the wrong problem. Okay. So what I mean with typically when an approximation is when I claim a boundary condition should be clamped somewhere, for instance, or the displacement should be zero somewhere, and it's only zero at parts of that, and other parts it sort of deviates a little bit from the zero. Although in spirit it's trying to get that. So that's what I mean with that. Okay. So let's go through this concept card and see what is involved. But this is really just making sure that you have a good understanding of conceptually what's going on. So if I give you the displacement field, I give you the geometry of the problem, and I give you the material. So I tell you what is the elastic material properties of the material that we're working with. Then you know everything. Okay, so the important thing is then you can tell me what is chopping with displacement boundary conditions, what is the tractions that were applied, where the tractions were non-zero that were applied, where were the tractions that were zero that were applied, is this thing in equilibrium, and all that type of stuff. Okay, so you can do the whole two, and let's just quickly walk through this, making sure that we're comfortable. So first off, displacement field this is now a vector field. So a vector of three fields, of three functions, the one U, V, and W. Then from this we can now compute the strain matrix. Okay, so this is the strain matrix that we can go and compute from this, and I'm just giving you here sort of the reminder of the Python's or the SymPy kind of tips. So just as a reminder to put something to flash in your brain. So derived by array. So how we take this displacement field is we use derived by array to compute the displacement gradients, this gradient of this U vector, and so this will be then three columns. The one column will be the gradient of U, the other column will be the gradient of V, and the other column will be the gradient of W. We take that displacement gradient, add its transpose, multiply by half, and that's the strain matrix. Okay, so this was that symmetric part. The spin part of the displacement gradient does not contribute towards strain. It just contributes towards a rigid body rotation. That's why we don't care about that. And it indicates all of this is small strain assumptions and small rotation assumptions. Okay, so there's the strain matrix. And now I can say, well, we know that this is symmetrical. So instead of having 9 components in the strain matrix, we can package them using the Voigt notation into a 6x1 vector. That's in any case what we need to do if we want to use the classical constitutive matrices, especially the matrices that are also supplied in the prescribed textbook. So let me maybe just quickly see if I can open up that prescribed textbook, just an example of that maybe quickly. So let me see if I can quickly do the open up this chapter 1, and just to remind you, if you want to use this all requires the Voigt notation, okay? Because if this was a matrix and this was a matrix, this would have to be in a different form. You would have had to do a double contraction. This would have been a fourth order tensor. You would have had to require to do a double contraction, sort of a double dot product, before you would have gotten that matrix out. This why things are simplified quite a lot this way. Okay, so let me just get out of here, get back to my slide. Okay, so that is just a reminder of this Voigt notation, and that's stuff that you were able to do quite comfortably. So that's what I'm just putting here, matrix to vector. And then we get the 6 stress components. So this by construction will be a symmetrical stress tensor, okay, because this is symmetrical, and then by construction this is symmetrical, and that also implies the types of materials that we have do not have embedded moments or pointwise moments that are present there. Okay, so that is the assumption that, and this is in any case, this is valid for 99.99% of materials. And just as a reminder, anyway, so let me just, okay, that's fine, okay. And then once we have that, we can now actually go and say, okay, let's check equilibrium by looking at the divergence of the stress tensor plus the body forces. That must all be equal to 0. Okay, this is now for the static case. If this was a dynamic case, there would still be terms regarding the density and acceleration, but because we're working with linear elastic and static case, we essentially can say that should be equal to 0. And this divergence of the stress tensor was just essentially the equilibrium equations that we derived. And this is just writing it in a bit more compact form. So this is the gradient operator dotted with the stress matrix. And then you can see essentially what we have is then a sum matrix. The dot product tells you we're going to sum stuff. So instead of having a matrix in the end, we're only going to have a vector. The one is the sum of forces in x, sum of forces in y, and sum of forces in z. And remember, sum of moments equals to 0 was the symmetry of the stress tensor. Okay, and then we should be able to check for prescribed tractions. Okay, and that includes now all tractions that we claim we've applied non-zero stuff, and also the stuff where we claimed we have applied nothing. We have to check all the surfaces. Okay, that is important. There's additional surfaces that we have to check, and that is where we have prescribed displacements. Okay, so I will make this point clear now when we look at the strong form again, but just as a reminder, when I have a structural mechanics problem, wherever I have a prescribed displacement, there will be a traction that will follow there. So to enforce that prescribed displacement, some force is going to be required. Okay, if I'm telling you I'm taking a ruler and I'm pulling it by 1 centimeter, and on one side and the other side is fixed, which if it's a rubber ruler, I would be able to do that. But the bottom line is where I'm holding that ruler, there's traction. Yeah, I'm giving the prescribed displacement at that one end by pulling it 1 centimeter, but there's a traction forming then. I can go and look at that reaction traction. Okay, so that is essentially important to understand, that where we have prescribed displacements, there's additional tractions we can go and check. Okay, but first off, this is just checking the stuff that we claimed we've applied. Okay, and then we have the prescribed displacements, and then we need to make sure that the prescribed displacements are what they claim to be. Okay, so if we claim that prescribed displacement here is so many millimeters or so many microns or so, then it needs to be, or if it's zeros on a face or 0 at a point, then we need to check that it's indeed true. And so the beauty is, just from this, yeah, so just from this we can reverse engineer and say, boom, strain, stress, check equilibrium, check the tractions, prescribed displacement. And so really what is important about this whole point here is If we just approximate the displacement field to a problem, we've approximated the whole problem. Okay. So if we get a displacement field that satisfies the problem, we've done all of this other stuff. And this is important also from the finite element context, that I want to make sure that I establish properly for you that this is why we will focus in the finite element method to approximate the displacement field in such a way that these things, and these things, and these things, and these things, and these things will be satisfied in some way. Okay, so hopefully that will give you already a good idea.